So in this video, I wanted to make another example regarding how we can solve AC circuits using nodal analysis. So in this example, we already have all the elements of the circuit represented as phasors or impedances. For instance, here we have a voltage source. Here we have another voltage source that has a value 40 with an angle of 60 degrees. I think that this 60 degrees is not very clear, so I will write it again, 60 degrees. Okay, so the idea is to think how we can represent, solve this circuit, using nodal analysis. So remember that for solving a circuit using nodal analysis, you need to apply um, the Kirchhoff current law to each of the nodes. Okay, so we can see here that we have one node right here, and also we have another node right here. So we have two nodes. We can say that this is also a node, but for this time, I will not count it for the analysis, but let's label this voltage in this node as V3. In fact, you can say that V3 minus the reference voltage, that is this one, no, this is the reference of the circuit, is equal to 0 volts, should be equal to the voltage of this voltage source, okay, that is 30 with an angle of 0 degrees, okay? So we can say that V3 is equal to 30 with an angle of 0 degrees. Okay, so this is like the way in which you can start solving the circuit. But first of all, aside from computing the voltage in this node, that I will label as node number 3, this will be node number 1, and this node number 2, you need to define the direction of the currents in each of the branches of the circuit. So for example, we can say that here we have a current I. I will label this as I1, and this current is flowing in this direction, no? From the voltage source of 30 with an angle of 0 degrees volts through the 4 ohm resistor. Also, we can have here another current that I will label as I2 that is flowing through the inductor. And here I3 that is flowing through this voltage source of 40 with an angle of 60 degrees. Remember that these are volts. And also we can have another current that is moving in this direction through the 2 ohm resistor that I will label as I5. And here we have another current that is flowing through this capacitor that I will label as I4. Okay, so remember that the first thing that you need to do is to apply the Kirchhoff current law to each of the nodes of the circuit. So here we have node number 1. And for node number 1, you can see that I1 is entering the node, and I2 and I3 are leaving. So that's why we define that the current I1 is equal to I2 plus I3, because according to Kirchhoff current law, all the currents that are entering a node should be equal to the currents that are leaving in order to maintain this equivalence. And what else? And well, we can say that I1 is equal to the difference in voltage between node number 3, that is the voltage V3, minus the voltage in node number 1 divided by 4 ohms. Okay, but we know the value of V3, that is 30 with an angle of 0 degrees volts, minus V1, and this is divided by 4 ohms. Okay, also we can compute I2, that is equal to the difference in voltage between node number 1 and the reference node, that is V1 minus 0 volts divided by J 4 ohms. Okay, and the problem here is that we cannot compute I3. Why? Because yeah, we know the voltage, but we don't know the resistance. Okay, so there is no way in which we can compute the resistance in this part. We only know the voltage, And also but we don't know the resistance in this part, okay? But let's stay with this information until now. We will compute I3 in a different way. But here we can face a problem, no? Because we need to define this Kirchhoff current law, but we don't know, we know the voltage of this element, but we don't know, or we do not have a direct way to compute the resistance or know what is the resistance through this branch in which I3 is flowing. Okay, so we need to deal with that in the case of this circuit. So for now, let's compute again the Kirchhoff current law, but for node number 2. So here you can see that we have I3 that is entering this node. I3 should be equal to the currents that are leaving this node, that are I5 and I4. So I3 should be equal to I4 plus I5. And well, we can compute I4. I4 should be equal, let me erase this. I4 should be equal to the difference in voltage in the capacitor, that is V2 minus the reference voltage, that is 0, and this is divided by minus J, 1 ohm. And this is equal to V2 divided by minus J times 1 ohm. And we have here I5. So I5 should be equal to the difference in voltage between node number 2 and the reference voltage. That is V2 minus 0 volts divided by 2 ohms. So I5 is equal to V2 divided by 2 ohms. Okay. So now, what we can do? Well, we can substitute all the values of the currents that we know. For example, for I1, we know that we have this value, so we can express this as 30 with an angle of 0 degrees volts minus V1. And this is all divided by 4 ohms. Okay. And this is equal to I2, that is equal to V1 over J times 4 ohms plus I3 that we don't know. This is for node number 1. And for node number 2, we have I3 that is equal to I4, that in this case is V2 divided by minus J1 ohm plus V2 that is divided by 2 ohms. Okay, so the idea is that, well, we don't know the value of I3, and we also we do not know the value of V1 and V2, okay? But here we have a relationship that describes the current in I3. So we can substitute this expression into our first node equation, that is the equation for node number 1. So we can say that 30 with an angle of 0 degrees volts minus V1, and this is all divided by 4 ohms. That is equal to V1 divided by J4 ohms plus I3, where I3 is all these terms. So we can place here I3, that is V2 divided minus J1 ohm plus V2 divided by 2 ohms. No? But we don't know the value of V1 and V2. But what we can do, if we go to the original circuit, you can see that the difference in voltage between V1 and V2 should be equal to this value. So we can say that V1 minus V2 is equal to 40 with an angle of 0 degrees, with an angle of 60 degrees. Okay, and these are volts. So here we have our system of equations, because we have here two incognitas, there is V1 and V2, but we have these two relationships that describes the relationship between the voltage and currents, and also we have this relationship that describes the current law, and here we are computing basically the difference in voltage that should be equal to the voltage that we have right here. So Well, let me only revise the procedure. Well, it seems that it is correct. So, based on these two equations, we can we can input this system of equations in your calculators, and you will find out that B1 is equal to 38.719903 with an angle of 69.6689 degrees, and B2 is equal to 6.75581 with an angle of 165.7166 degrees volts. Okay, so I think that that is all the results that we have. And mm, well, that is the result. No, this is the value of V1 and this is the value of V2. Okay, so this is what some people call a supernode. And the reason they say that it's a supernode is that, well, you need to define a bigger expression for the Kirchhoff current law because there is no way in which you can compute the current I3 directly. That's why you need to increase the size of the node in some way in order to generate a single expression as the one that we obtained by substituting I3 in the original equation for node number one in order to get only one equation that describes the Kirchhoff current law in the circuit. Okay? And well, we can find also a relationship that describes the interaction between V1 and V2 based on the difference in voltage between these two nodes and the voltage that we know, that is this voltage source of 40 with an angle of 60 degrees. So I think that's all for this example. I hope that you find it useful and see you later.